Hello, everyone. I think now is the time. Welcome to the non-volatile memory session. And this session includes four papers. The first one is improving the performance of NVM crash consistency under multi-core. The second one is more space may be cheaper. Multi-dimensional resource allocation for non-volatile memory-based cloud cache. The third one is ISO tree, a B plus tree with intra-cache line sorted leaves for non-volatile memory. The last one is loop to recursion, compiler assisted while leveling for non-volatile memory. During the presentation, the audience can ask questions by typing on the chat window. At the end of the presentation, I will collect those questions and present to the speaker. So now let's start with the first paper, improving the performance of NVM crash consistency under multi-core. The presenter is Zhiyuan Lu. He is a PhD student of computer science of Michigan Technology University. Now, let me start play the video.
Hello everyone, I'm Zhiyan Lu. Now I'm going to introduce our work improving the performance of NVM crash consistency under multi-core. The first is the background, including NVM crash consistency, ADR, and LAD. The main issue in NVM system is to keep crash consistency, which means that the system is recoverable to consistent state after feature, like power loss. Consider the example to insert a node C to the linked list. First, the next pointer of C points to B. Then change the next pointer of A to C. If crash happens on this step, without support of crash consistency, this list will be broken and in inconsistent state after recovery. For ADR, it's a synchronous DRAM refresh, which is proposed by Intel to safely persist write request in memory controller to NVM in case of power failure. As we can see, the red buffer supported by ADR, here we call ADR buffer, is in persistence domain. Recently, LAD proposes a logless crash consistency scheme if the size of transaction is smaller than ADR buffer. To achieve this, transaction updates accumulate in ADR buffer during execution and are flushed to NVM when transaction ends. Here is the example. It is assumed that ADR buffer size is 4, and there are 3 unique updates, W1, W2, W3, in transaction T1. As we can see, updates first accumulate in ADR buffer, then reach transaction end. Right now, suppose there is a crash. With the ADR support, contents in ADR buffer can be flushed to NVM safely. However, LAD falls back to log if ADR buffer overflows during execution. Our motivation is based on the shortcoming of LAD and consider the concurrent transaction execution under multi-core. Based on former assumption, we introduce another transaction, T2, which has 5 unique updates. In the first case, updates from T1 and T2 admitted to ADR buffer concurrently, and when T1 sends T1 W3, ADR buffer overflows. So in this case, we need to log T1 and T2. This causes 8 log writes. Next, we admit T1 and T2 to ADR buffer sequentially. First, T1 updates accumulate in ADR buffer, and then T1 ends. Contents in ADR buffer can be flushed. Then T2 comes. It causes ADR buffer overflow. In this case, we only log T2, which is 5 log writes. As we have seen, with suitable admitting scheme, there is no necessary to log T1. Based on these 2 examples, we found that first, concurrent transactions compete for limited ADR buffer. Second, ADR buffer ADR buffer contention causes many unnecessary logs, such as T1 in the first case. Our experiment shows that there are many unnecessary logs. It can be 59.5% and 28.3% in average. Based on our observation, we propose this virtual ADR cooperated with ReduLog. Virtual ADRs are private SRAM buffers for each core in memory controller. I will use formal example to show how our design avoids unnecessary log for concurrent transactions. In the first, updates from different core enter their virtual ADR. T1 ends without virtual ADR overflow. Its updates are sent to ADR. However, T2 exhausts its virtual ADR and has to perform logging without consuming ADR. In this case, we adopt ReduLog because it enables faster commit speed. We compare our design with that, and we can see in the first graph, virtual ADR almost eliminates all unnecessary log. For performance, ReduLog improves throughput by 20.1%. Virtual ADR with ReduLog improves throughput up to 78.6% and 36.2% in average. In this work, we observed that there is a significant amount of unnecessary log under multi-core in LAT. So we proposed a design which avoids unnecessary log for concurrent running transactions. To do this, virtual ADR is introduced to filter transaction with large red set. To further improve performance, we adopt ReduLog, as we have eliminated most of log operations up to 94.9% compared with that, and virtual ADR with ReduLog increases transaction throughput up to 78.6%. This is all work we have done. Thanks for your listening.
Okay. Hi, Zhiyuan, please unmute your microphone.
Okay. Hi. Yeah.
Yeah, let me see whether there are any questions. Is there any question from audience side? Seems there is no question from the chat session. Then I think I have a question for you. Like, could you explain why LAD need to do log?
In that, you know, when ADR buffer is exhausted during the transaction execution, ADR buffer should not be should not flash its content to if crash at this time. Otherwise, the transaction will be partly updated. So in this case, data is volatile. So to ensure crash consistency, LAD has to do log in this case. Yeah.
Okay, thank you. Now let's move to the next presentation. The next one is mouse space may be cheaper. Multi-dimensional resource allocation for NVM-based cloud cache. The presenter is Ning Bao. Ning Bao is a PhD candidate in the Department of Computer Science at Renmin University. Her research interests include emerging storage technology, cloud computing, and cache systems. Now let me start.
Hello everyone, I'm Ning Bao from Renmin University of China, and I'm honored to present our paper, More Space May Be Cheaper, Multi-Dimensional Resource Allocation for NVM-based Cloud Cache. This is the overview of my presentation. First, I will introduce background and motivation. Then we will have a look at the framework of our algorithm called MECC, followed by experimental result. Finally, it is the question and answer time. We have entered the big data area now. The total data volume has increased more than 30 times from 2009 to 2020. As a result, there are huge IO demands, and more users choose cloud to satisfy their demands. Lots of cloud platforms are available nowadays, and I only list a few of them. Cloud Cache can boost I/O performance of cloud users significantly. Look at the example. Many cloud providers choose to distribute some cache devices geographically close to clients. So many I/O requests of the clients can be served by the high-speed cache with low I/O latency and low network latency. So the total I/O performance is much optimized. Such scheme is popular among clients like database and web servers. Moreover, NVM devices are popular as cloud cache for their large capacity, good I/O performance, and also reasonable price. So we focus on NVM-based cloud cache. What is the problem of NVM-based cloud cache? First, we look at cloud cache. There are two main objectives of cloud cache: SLA, short for Service Level Agreement, and cost. SLA means that the service providers and users have reached an agreement on what service and what service quality the user will be served. Service providers need to ensure SLA. And for cloud cache, SLA usually means that the user will get the same performance as given the ensured cache capacity. Cost is crucial for cloud. Service providers with lower cost can provide lower price or make more interests. But can NVM satisfy the two objectives? Many NVM devices have the write endurance problem, making them difficult to satisfy cost. Write endurance problem means that every I/O unit on the device tends to be unreliable if the unit is updated too many times. If we write at the full write bandwidth of the mainstream NVM devices, these devices will be worn out in 8 to 85 days. But their expected lifetime is 3 years, so 8 to 85 days compared with 3 years. And when such devices need to stand high write pressure, like working as cloud cache, the devices need to be replaced frequently, resulting in high cost. If we categorize these algorithms into two types, DRAM-based and NVM-based algorithms, and we apply them into NVM-based cloud cache, will they satisfy the two main objectives, SLA and cost? For DRAM-based cache of RAM, so cost is unsatisfied. Most NVM-based cache algorithms the performance is unpredictable, so the cost is reduced, but SLA can be ensured. Our MECC is aimed to satisfy SLA and cost at the same time. How can we do that? We have found that the cost bottleneck of cloud cache is the device replacement. Let's look at the example. The red small squares stand for hot data and the green ones stand for cold data. Cache can't ensure only cache hot data, so there are two colors in cache. We compare two different scenarios and suppose one NVM device is 1 TB. Then it is 1 TB versus 2 TB. Our intuition says that the larger space is more expensive. But let's see what will happen for NVM-based cloud cache. If we buy one NVM device at first, the device is not big enough to keep all the hot data. Then the hot data in cache and out of cache will be exchanged frequently, leading to high write pressure. So the device is worn out much earlier before its lifetime. Let's assume it's worn out in 1 year. We need to buy 3 devices in 3 years. To simplify the question, we assume that the price keeps the same in the 3 years. So the total cost is 3 devices. If we buy 2 NVM devices instead of 1, the hot data can be kept in cache now, and we can easily cut the writes, but the performance is still satisfactory. So the 2 devices can survive 3 years, and the total cost is only 2 devices. So we come to an innovative conclusion. More space may be cheaper. If we have a larger space with lower writes, it can satisfy SLA and also reduce cost. And this is the basic idea of MECC, short for Multi-Dimensional Resource Allocation Enabled Cloud Cache. For each tenant in MECC, there are 2 important parameters, P and cache size. All the missed data have the probability of P to enter the cache. P controls the writing amount. In other words, MECC treats cache capacity and NVM writes as 2 independent resources to allocate. The shape of each tenant's cache can be changed to all the directions to find the best solution. This is the total framework of MECC. Each tenant has a tenant manager to control the cache and also predict the performance of potential schemes. Tenant manager sends the potential schemes which satisfy SLA to the global manager periodically. The global manager will collect the potential schemes and compute the best scheme. We conducted experiments with real-world traces replayed on real NVM devices. The x-axis is the relative capacity of SLA, and the y-axis is the relative cost of the baseline. The baseline of the cost is given the capacity of SLA and runs normal LRU on it. The static scheme means that we only increase the capacity but runs LRU on it. It's used to show the effect of only increasing the capacity. For page limit, we can't show all the detailed results, but the SLA of every tenant is satisfied in all the cases. We can see that the cost of MECC reduces about a half in all the cases. Moreover, the cost saving of static is not much, which means that only increasing the cache capacity has little effect on cost, and the algorithms of MECC are efficient to allocate appropriate cache capacity and write amount to each tenant. That's all. Thank you for listening. I'm looking forward to your precious questions.
Yingbao, please unmute your microphone and
Yes.
see whether there is any questions.
Okay.
I didn't see anything from the chat window. The audience pretty quiet today. And then I have a question for you. Like, how does the global manager compute the best solutions?
Oh, yes, this is an optimization question. We have the limited condition, which is the total device capacity, and we want we want to minimize the total cost. The challenge is that it's difficult to get the correct mix ratio curve in a 3D space with changing capacity and updating parameter p. So we have to pass all the potential schemes to get the best solution.
Okay, thanks. Now let's move to the next paper. The next paper is IO tree, a B+ tree with intra-cache line sorted leaf for non-volatile memory. The presenter is Chundong Wang. Chundong Wang is an assistant professor at Shanghai Tech University. His research interests include data storage, non-volatile memory, and computer architecture. Now let me play the video.
Hello everyone, this is Chundong Wang from Shanghai Tech University. Today I will do a presentation about IO tree we have developed for non-volatile memory. Non-volatile memory has both DRAMs and disks characteristics. That's why many companies are developing NVM products. Today, Intel's Optane DC memory is commercially available. This is a diagram of the computer architecture. We have the CPU cache, we have the DRAM, we have the disk. For this system, we need to guarantee the correct consistency of data, which means the data can be recovered to a consistent state in case of a system crash, for example, a power failure. For the on-disk data, the correct consistency can be achieved through logging or compare on write. Now with using the non-volatile memory, we can reshape this architecture in this way. So however, now the data in NVM will be directly operated by the CPU, and we know that the memory operations between the CPU cache and the memory are hardware controlled. So this will bring new challenges for us to guarantee the correct consistency stored in NVM. So let's see a classic architectural challenge for in NVM data structures. It is reordered writes. So what does this mean? So assume that we have a program which wants to write the data x, y, z in this order to the non-volatile memory. But when the CPU truly writes some data, such data to NVM, it may reorder the writing order. In this way, z, x, y. This is possible. However, these reordered writes are not good for consistency. Assume x means we create a new tree node, and z means we record the node's pointer. This is quite common for a B+ tree. After we write the data z, the system crashes. So what we will have? We will have a dangling pointer z. However, the x is not successfully created. So this will cause inconsistency. Luckily, we have instructions to maintain a writing order, which is cache line flush and memory fence. Cache line flush will flush the data to memory, and memory fence is a barrier that will demand memory operations after an M fence cannot proceed until memory operations before it complete. So with this cache line flush and M fence, we can rewrite this program. However, we can maintain the writing order now. but the cost of memory fence, the barrier, and flushing the data to non-volatile memory is non-trivial. So we need to reduce the use of cache line flush and memory fence as much as possible for high performance. As to the B plus tree, it is a classic indexing structure. We have the internal nodes, we have the leaf nodes. So the keys in the internal nodes and the leaf nodes are all sorted, as you can see from this example. So this is the classic B plus tree. And for the B plus tree and the non-volatile memory, there are several state-of-the-art. For example, the CTDH tree, which are with sorted KV pairs in the nodes. We also have NV tree and WB plus tree. Both of them are with unsorted key value. Later, we have IP tree. It also has unsorted key value pairs, but with fingerprints to accelerate searching. Now we have fast and fair and circuit tree. They are with sorted key value pairs. They use the store dependencies to reduce the use of cache line flush and memory fence. Let's use the fast and fair for example. So this is a sorted node, as you can see, and we want to insert this 20F. So what we will have, because we want to keep the node sorted, so we need to sift the key value pairs, and then we insert the 20 here. So this is the sorted nodes. From this one, we can assume that 4 key value pairs will occupy one cache line. So in this example, we modify 2 cache lines. So this is one cache line, this is one cache line. Both of them are modified. So we will flush 2 cache lines. So you can see that to keep a node fully sorted, will make multiple key value pairs to be sifted for insertion and deletion, and more KV pairs sifted. That means more cache lines are modified. So more cache line flushes will be called. So that means worse performance, worse insertion and deletion performance. So this drawback of sorted nodes for the insertion and deletion. On the other hand, so when we keep a node unsorted, when we insert the new key value pair, so we like NV tree here, we only just append the key pair here. So we only modify this cache line. So we just need one cache line flush. However, so that means the insertion performance is quite good for unsorted nodes. However, the search performance is not good. Let's assume that we want to search 20. We need to do 6 comparisons. We can find the key. So the search performance is not good. Although for FP tree and WB plus tree, they introduced acceleration techniques, and our study will show that such techniques are not so efficient, not so free of charge. Based on such observations, we developed a semi-sorted node. So what does this mean? So this is the fully sorted node, and we will keep each cache line sorted. However, the whole node is semi-sorted. This is an example. We can see this cache line is sorted, this cache line is sorted, but the whole node is unsorted. So with this intra-cache line sorted leaf nodes, so when we do the common insertion, we only need to flush at most 1 cache lines of key value pairs. How we can do that? Let's assume we will insert this new key pair to this node. So we just first find this cache line that has vacancies. So we sift this key value pair, we insert this new one. And because we only modify this one cache line, so we just flush this cache line and we put the new key value pair. This will finish the insertion. So as you can see, just one cache line, we can finish this insertion. We just flush one cache line of key value pairs. And this is a cache line. And for the search, we will use some algorithm called linear search with hops. What does this mean? Let's see. We want to search the 20. So what we will do? We will compare here, and we find that 15 is less than 20. So we go to next element. However, here we find that 32 is larger than 20. Because this cache line is sorted, we know that 20 will not exist larger than 22, already than 20. So we just jump to the next cache line. And then at here, we find our target. So from this example, you can see that to search KV 20, we just this the core of the core design of the IoT, the intro cache line sorted leaf nodes, and more details about multi-threading crash recovery can be found in the paper. We have compared IO3 to state-of-the-art B plot tree. We used many workloads. Here I only show some workload following the uniform distribution for the standalone B plot tree. This is the insertion performance. This is the average execution time. From this diagram, you can see that the execution time of state-of-the-art are much longer than IO3. That means IO3 achieves much higher insertion performance. Similarly, for the search performance, the execution time of IO3 is much shorter than state-of-the-art. That means the search performance of IO3 is also very good. Now let's make a conclusion of IO3. It is a B plot tree developed for NVM with intro cache line sorted leaf nodes. For common insertion and deletion, we only need to flush at most one cache line of key value pairs. And for search, we have the linear search with hops to reduce the comparisons. That's why IO3 can achieve both good insertion and search performance. Thank you very much. Now I would be glad to answer your questions.
Okay, is Chundong here?
So this is Sudipta. Can you hear me?
Oh, yeah.
So this is actually, I'm the co-author. Chundong could not attend today for some reason, so I am covering for him.
Oh, okay. Okay, then like the question is, if you had experimented with real hardware, do you think your conclusion will be different?
So we doubt that it would be different because the idea of this semi-sorted cache node, that the nodes are sorted within a cache line, is quite fundamental. But that said, of course, we did not experiment with the real hardware, so I cannot directly make any conclusion. But it's unlikely to be different.
Okay, thank you. Okay, now let's move to the next paper. The next paper is Loop 2 Recursion, Compiler-Assisted Warehousing for Non-Volatile Memory. The presenter is Wei Li. Wei Li is a master student in School of Computer Science, Wuhan University. His work focuses on warehousing techniques in PCM-based memory system. Now let me
everyone. Welcome to my talk, Loop 2 Recursion, Compiler-Assisted Warehousing for Non-Volatile Memory. I'm Willie, master student from Wuhan University. All nowadays, non-volatile memory technologies have been considered as a promising candidate to replace DRAM stability and DRAM comparable read-write performance. However, the limited writing endurance of NVM presents challenges for its application. As shown in the table, the writing endurance is only 10 to the 7th to 10 to the 9th. Endurance limit is only one and 201 times. For each execution of the extra, each stack frame is each stack goes problem by transfer. The code snip on this slide is equivalent to the previous example. It replaces the loop with the recursive function main loop. Distribution of the function stack frames. It's obvious that the stack frames are much more evenly distributed. On the right top shows that in the recursive function, the variables I and j only needed to be written for 1 and 2 times. In conclusion, recursion assumes much better well-leveling performance. Based on the motivation, we propose the loop to recursion, which automatically transforms loops to recursions at compile time. Loop to recursion mainly includes 3 parts. First, given a loop, we'll make an analysis and decide whether or not to transform this loop. Then, the process of transformation can be further divided into the 3 steps: the preparation for transformation, generating recursive function, and replacing loops. Lastly, when loop includes some point operations, we make some special handlings. Now, I'll give more details about these parts. First is a loop analysis. Considering that loops tend to be more efficient in running than recursions, we try not to transform those loops that will certainly not lead to the uneven wear on the stack. As we just discussed, loops cause uneven wear due to containing variable rights or function calls. Therefore, we only transform a loop where a loop meets at least one requirement: there are variable rights occurring on the stack or their function calls is contained inside the loop. Perform loop transformation. The first step of transformation is preparation. We prepare the parameters and return values for the recursive function to be generated. For parameters, as loops tend to use variables defined outside, like I and j in the example below. After transformation, these variables are not accessible inside the recursive function. Therefore, they must be passed as arguments in the course to it. For return values, as we pass the arguments by value, the updates for the arguments in the recursive function will not affect their value in the original function. Therefore, if some variables are still used after the loop, we return them and update them in the original function. Now, we have got parameters and return values. We can create a recursive function with the corresponding parameters type and return type. We need to ensure the equivalence between the original loop and the generated recursion. Therefore, we need to maintain the consistency of the control flow. We mainly made the following modifications. When loop condition holds, which means the loop would perform the next iteration, we make a recursive call in the recursive function instead. Otherwise, when loop condition doesn't hold, the loop would terminate. Correspondingly, we return from the recursive function. Lastly, after generating the recursive function, we can now remove the loop and call the recursive function instead. We pass the needed arguments and perform necessary assignments for return values. And at this point, we have successfully transformed a loop to recursion. However, hold data issue may still remain when loop updates pointers pointy. For example, the loop in the left iteratively dereferences pointer p and increments its pointer I. I is the hold data. After transforming the loop to recursion, pointer p will be passed as argument, but all the store operations still perform on i's memory location, resulting in a failure for eliminating the hold data. To solve this problem, we copy the pointer before the recursive call in the recursive function. As shown in the right code, we'll use a reference to the copied variable as the argument in the recursive call instead of the current pointer. When the call returns, we copy the value back. By transforming loops to recursions, we can achieve better well leveling, but it may substantially increase the stack memory's consumption. Without any control, excessively deep recursions may exhaust all the available stack memory. Therefore, we also propose to optimize stack memory usage for loop to recursion. When generating a recursive function, we can limit the depth of the recursion. An extra parameter depth is added to the recursive function representing the depth. It's initialized with 0 when the recursive function is first called and incremented by 1 in the following recursive calls. When depth reaches the depth limit, the recursive function returns. After limiting the depth of recursion, the distribution of stack frames is assumed in the right figure. We can see that the stack memory usage used by the recursion is reduced several-fold. What's more, by adjusting the depth limit, we can trade off between well-leveling performance and the stack memory usage. Next is the evaluation section. We evaluate loop to recursion in terms of well leveling, performance, and stack memory usage. We implement loop to recursion based on LLVM. It operates on a low-level intermediate representation and thereby is applicable to various programming languages. In our experiment, we set the recursion depth limit to 20. We compare loop to recursion with the baseline without well-leveling management and the state-of-the-art well-leveling approach, dynamic stack, which uses a dynamical allocator to allocate stack frames when program running. We select some applications from my bench for evaluation. By the worst severe degree, to evaluate well-leveling effectiveness, we compare the number of writes on the hottest memory address. We can see that both the dynamic stack and the loop to recursion significantly decrease the write count compared to the baseline. On average, loop to recursion reduces 90% and 50% of the maximum write count compared to the baseline and the dynamic stack, exhibiting higher well-leveling effectiveness. To evaluate the performance, we evaluated the total number of instructions executed, and the normalized result is shown in the figure. The dynamic stack incurs significant performance overhead, which comes from additional allocation and deallocation operations for dynamically allocating stack frames. Compared to the dynamic stack, loop to recursion has substantially lower performance overhead. Then we compare the stack memory footprint to evaluate the memory usage overhead. We can see that the stack memory overhead caused by loop to recursion is much lower than that caused by the dynamic stack. On average, the stack memory consumption of loop to recursion is about 1.47 times that of the baseline, which is somehow tolerable considering that the PCM memory provides much higher storage density. At last, let me just run over the key points again. OVM is considered as a promising replacement for DRAM, but its limited write endurance poses lifetime challenging. Considering that loops in programs cause uneven wear, we propose loop to recursion, which automatically transforms loops to recursions to solve this problem. The experiment results show that our approach exhibits better well-leveling effectiveness with lower performance and the stack memory usage overhead. That's all. Thank you.
Okay, I think we can run out of time now. So I won't ask any question for the last presentation. So that's all about this session. And Thanks for attending and hope you enjoy the rest of the conference. Thank you.
Thank you.
Okay, thank you, Chiwan, for coordinating this session. So we're going to end this session and get prepared for the next one. Thank you so much again.